Hello everybody, this is the video for lecture 23, and today we are going to finish chapter 23. In the last video we learned all about how mirrors can create images because of the ways they bend light. Mirrors do this because of reflection. However, lenses can do something very similar. When light enters a lens, the light refracts and it bends. So in much the same way that mirrors can create images, lenses can also create images. Basically, any type of glass or plastic that light can refract through can be considered a lens. So you have light come in, it refracts into the lens, and then it refracts again as it leaves. The lenses that we will be considering will be called thin lenses, and they will have spherical or flat surfaces. So these curves on the outside here will be considered parts of a sphere, and flat surfaces are also acceptable. We call them thin for kind of a technical reason. Basically, we don't want to consider these 2 points of refraction. We want the light to enter the lens and refract once. At least that's what we want to consider. Also, this avoids any sort of weirdness where it refracts like outside the side of the lens. Just like with mirrors, you have 2 types of thin lenses. The first type, the kinds shown at the top, are the kinds that will take horizontal light rays and converge them together. These will be called converging lenses. The second kind, such as shown at the bottom, will take horizontal light rays and diverge them. These will be called diverging lenses. Notice that for lenses we also have the terms concave and convex. The concave lenses are the types that go in like a cave, and the convex lenses are the ones that bend outward. Concave and convex are very similar to the definitions we had for mirrors, but note that with mirrors, it was the concave mirror that was a converging mirror, and a convex mirror that was the diverging mirror. These 2 relationships are flipped with lenses, so it's probably easier just to stick with converging and diverging lenses. So the converging lenses take horizontal light rays and focus them all onto a single point. And the diverging lenses take the horizontal light rays and diverge them away from each other. If you trace back the outgoing rays for the diverging lenses, they will all meet at a single point. This will be the focal point for the lens. So the big difference with lenses and mirrors is that with a mirror, light can only strike the mirror from one side. But with a lens, light can enter from either side. So if instead of these blue rays, I had horizontal rays entering the lens from the right side, the lens would bend these horizontal rays toward a point on the left side of the lens. For this reason, we need 2 focal points for each lens. One will be on the left and one will be on the right. And this is true for both converging lenses and diverging lenses. So the focal point is where the horizontal light rays meet, or would meet if you trace them backwards, and the focal length is the distance from the center of the lens to the focal point. These are the exact same definitions we used for mirrors. So then, quick question. You have a lens in the center of this diagram. On the left side, you have a candle, and the candle flame is emitting one particular light ray that's heading horizontal to the right. That light ray passes through the lens. Of the rays shown, which one best represents the outgoing light ray? Think about it, and I will give you the answer during one of our meetings. The setup for this next question is the same, but it is a bit trickier. So instead of considering the horizontal light ray that's coming out of the candle, in this question we're going to consider the one specific light ray that travels through the focal point on the left side of the lens. Once that light ray refracts in the lens, which of the four rays shown will best represent the outgoing ray? So this question is a bit trickier, but you do know enough at this point to figure it out. So think about it, and I will give you the answer during a meeting. Okay, for this question, I'm going to exit full screen so I can use my ruler. And basically, I'm going to have to give you the answers to the previous questions. So if you haven't thought about them yet, please go back and think about them. The ray that starts horizontal and then hits the center of the lens will actually refract through the focal point of the lens. This is basically the definition of focal point. So this one starts horizontal. The outgoing ray refracts through the focal point. The ray that starts at the top of the candle and goes through the focal point on the left side of the lens will refract and end up being horizontal. So the outgoing ray in this case would look like that. And then to answer this question, you basically have to remember what the definition of image is. Remember that an image is where the outgoing rays meet or where it looks like they're coming from. So that's basically what you have to figure out to answer this question. I will let you think about that and give you the answer in a meeting. And by the way, to understand why this lower ray becomes horizontal after it refracts, you have to think about the ray traveling backwards. So instead of starting on the left and traveling to the right, imagine that it's a ray that's starting on the right side and it's traveling horizontally to the left. After that horizontal ray refracts, it will refract through the focal point of the lens, and it will end up at the top of the candle. As the questions on the previous few slides hinted at, lenses also have ray diagrams. And luckily, the three easy-to-draw rays for lenses follow the same rules as with mirrors, although the diagrams themselves look slightly different. So we start with the horizontal ray, the ray that starts at the top of the candle and goes horizontal until it hits the lens. Now this is a converging lens, so after that ray refracts, it will bend toward the center of the lens, and based on the definition of the focal point, it will pass through the focal point of the lens. So the first easy to draw ray is the horizontal to focal point ray. The second easy to draw ray starts at the top of the candle and passes through the focal point on the left side of the lens. After this ray refracts, it will refract so that it's horizontal. So then the second easy to draw ray is the focal point to horizontal ray. And the third easy to draw ray starts at the top of the candle. It passes straight through the center of the lens, and then it exits outward. So the third easy to draw ray is the one that just passes straight through the center without bending at all. Now, if you've drawn all of these correctly, then all of the outgoing rays should meet at a single point. In this figure, it's about right here. That point where all of the outgoing rays meet is the image location. So this lens forms an image of the object at this position. Note that in some cases you may have to trace back the outgoing rays to make them meet. We will see examples of this coming up. This question actually just gives me an opportunity to draw another ray diagram for you. Remember, with mirrors, there were two cases for a converging mirror, where the object was outside the focal point and where the object was between the focal point and the mirror. We also have this with converging lenses. So in this question, we're asked to find the image position if the object is between the focal point and the lens. We will start by drawing the first and third easy to draw rays. So the first one is the horizontal ray, and nothing changes here. After this refracts in the lens, it is a converging lens, so it refracts toward the focal point. So that is the first easy to draw ray, with the outgoing ray heading to the right there. The third easy to draw ray is as simple as it sounds. It starts at the top of the candle and it passes right through the center of the lens, and it doesn't refract at all. So that's the third easy to draw ray. Now you'll notice that these two outgoing rays are spreading apart. So they're never going to meet, and they'll never form an image on the right side of the lens. In order to find out where the image location is, we have to actually trace back these outgoing rays to see where it looks like they were coming from. So we trace back that one, and then we trace back the first easy to draw ray. And we can see that it looks like they'll meet about right here. Let's make that green. So that means that when the object is located between the focal point and the lens, the image actually forms on the left side of the lens. And in this case, it's right about at this location. So that's enough to answer the question. We drew the first easy to draw ray, which was the horizontal to focal point ray. We drew the third that passed straight through the center without bending. But what about the second easy to draw ray? Okay, this one is a bit different because instead of starting at the candle, it has to look like it's starting at the focal point. So it has to look like it's starting here. Then it would actually start at the candle and head in this direction. Okay, but the ray that I'm drawing right here looks like it might have been coming from the focal point. When this ray refracts in the lens, it will refract horizontal. So this is the second easy to draw ray in the case of an object that's between the focal point and the lens. Note that this ray is also not going toward the first and the third ray. All three of these are spreading out. In order to find out where the image would be, you would have to make or trace back that outgoing ray to see where it looks like it's coming from. And you'll notice that all three of the rays, when traced back, meet at just about the same location. That's the image location. In this question, you have a ray that starts at the candle and it heads toward the focal point on the right side of the lens. Notice that this is not one of the easy to draw rays. In particular, it's not the second easy to draw ray, because the second one starts at the candle and passes through the focal point on the left side of the lens before it refracts. So essentially, this is just some random ray. Now there's two ways you can go about answering this question. The first way is the easy way. You just follow the ray as it's going toward the lens, and then you note that it's a converging lens, so you think about which direction the ray should bend after it refracts. knowing that a converging lens will always bend rays toward the center of the lens should give you the answer. The second way to answer this question is a bit longer, but it's also good practice for drawing ray diagrams. So let me go back 2 slides, back to this one where we found the image location on the right side of the lens. So here I've drawn 3 outgoing rays, but note that every ray that starts at this object and passes through the lens will also pass through the image location. So for instance, if I draw a random ray that passes through the top of the lens will refract this ray so that it passes down through the image location. Similarly, if I draw a ray that passes through the bottom of the lens will refract the ray so that it refracts up toward the image location. Okay, so then if you go back to this question and you draw the ray diagram with 2 of the 3 easy to draw rays, you'll find the image location. Once you have the image location, every ray that passes through this, that starts at the object and passes through the lens, will pass through that image location. So this green ray in particular will bend to be one of these 4 rays, but one of these 4 rays will also pass through the image location. So think about that, and I will give you the answer during one of our meetings. Diverging lenses also have ray diagrams, and luckily they follow similar rules to all the other ray diagrams. So the first easy to draw ray will start at the top of the candle. It will go horizontal toward the lens. Now this is a diverging lens, so every ray that passes through it will diverge away from the center. To find out which direction it actually diverges, you have to make it look like the outgoing ray is coming from the focal point on the left side of the lens. So this is the first easy to draw ray. The second easy to draw ray starts at the candle. It starts going toward the focal point on the right side of the lens. When it refracts in the lens, it refracts away from the center. And this one will refract so that it goes horizontal. This is the second easy to draw ray. And the third easy to draw ray is the same as in the converging lens case. It starts at the candle, it passes straight through the center of the lens, and it doesn't bend at all. So this is the third easy to draw ray. To find the image location, we have to find the point where it looks like, or where the rays, the outgoing rays, actually meet. So in this case, I've already traced back the first outgoing ray. The second outgoing ray looks like it's coming from this direction. And the third easy to draw ray I don't actually have to trace back because it passes right through the location that I'm looking for. Again, if drawn properly, all of these rays should look like they're coming from one location. That location is right here, and this is the image location. So a diverging lens forms an image of the object on the same side of the lens as the object. Also, it's a virtual image because not all of the rays actually meet at the image location. Thin lenses also follow this lens equation. In fact, this is what it's named for. And luckily, it's the same equation that we use for mirrors. So you have 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. For converging lenses, we will always get a positive number for the focal length. For a diverging lens, the focal length will always be a negative number. The majority of the situations we're going to consider will be a real object, so we will almost always take p greater than 0 for the object distance. That's the distance from the object to the center of the lens. Q is the image distance. If it's a real image where all of the outgoing rays actually meet, then Q will be a positive number. If it's a virtual image where you have to trace back the outgoing rays, Q will be a negative number. And then, final technical note, all of these values, F, P, and Q, are always measured from the center of the lens. For us, this isn't actually a problem because we're talking about thin lenses, so essentially we're already considering them thin enough to only have just that center part. But when you're doing diagrams, ray diagrams, you always have to measure from the object to the center of the lens, or the image to the center, etc. And magnification for lenses works the same as for mirrors as well. We define the magnification as the image height divided by the object height. And then using geometry, you can show that this is equal to minus Q over P. Again, with lenses, you do have to be careful with this minus sign, so make sure that's in there. For lenses, H will always be positive for an upright object and negative for an inverted object. This is the same as with mirrors. And it's also the same for the image height, positive for an upright image, negative for an inverted image. And again, same as mirrors, if the absolute value of M is greater than 1, then you have an image that has increased in size. If it's less than 1, then it has shrunk in size. The absolute value we're using here, because we only care about the magnitude of the magnification, the minus sign simply tells us whether or not the image is upright or inverted. In this question, you start with an object. At one of these 5 locations, you have a lens. You don't know what type of lens it is. It's either converging or diverging. The object and that lens form this image. The question asks you to find which position the lens is at, and also what kind of lens it is. Finding the position of the lens is actually kind of simple, because in both the converging and diverging lens case, notice that the third easy to draw ray always gives you a line that connects the object, the image, and the center of the lens. Okay, so then knowing where the position of the lens is, to determine what type of lens it is, I think the easiest way to do that without knowing the focal point is to compare the ray diagrams that we've already drawn. So think about this question, and I will give you the answer in our meetings. Here is a table that summarizes the rules for lenses. And I've actually adjusted the wording on the table so that all of these rules apply to both mirrors and lenses. So for example, if you have a converging mirror or lens, in this case, F would be greater than 0, and you have an object that is between the focal point and the mirror or lens, then the image will be virtual, the image will be upright, and you'll have Q, the image distance, is less than 0. So that means Q is a negative number, and this tells you that the image is not on the outgoing light side. For a mirror, the outgoing light side would be the left side. You have light reflect off the mirror and head to the left. For a lens, the outgoing light side would be the right side. When the light refracts in the lens, it refracts and heads off to the right. So in any case, this is just a handy table that you can, keep next to you while you're working on homework or exams. The reason we talk about objects and mirrors and lenses and images is because mirrors and lenses can be used to create images at different locations from the object. For example, with that mirroscope, you have an object that's located at the bottom of the flying saucer, but an image is created at the top of the flying saucer. Lenses can do something similar, and that's what this question's getting at. So in this question, you have an object located at position P. You have a lens located in the center. Notice that it's a converging lens. You can tell this by the shape of the lens. And then you have an image that's created on the right side of the lens. It is a real image because all of the outgoing rays, all of these rays are passing to the right. All of them actually do converge at the image location, and it's inverted because it's upside down. The question is, where would you stand to view the image? Now I want you to think about it, but let's rule out one of the answers. So let's look at answer C. Standing at point B facing to the right. So then you would be standing right here and you would be looking to the right. Okay, so if you're in this position and you're looking to the right, you are looking toward the image location, but note that all of the light rays that are coming from the object are not entering your eye. They are instead hitting you in the back of the head. Okay, so that hint tells you that the light rays actually have to be entering your eye somehow. So think about that, try to figure out the answer, and I will tell you in one of our meetings. This question has the same situation, but it is using a diverging lens. The same hint as the last slide applies, so the light rays do have to be entering your eyes. But let's rule out another answer here. Let's look at answer B, point B facing left. So now you're at point B and you're looking to the left. So again, you are looking toward the image location. This time the light rays are actually entering your eyes. They start at the top of the object and they do go straight into your eye. But where does it look like these light rays are coming from if you're at point B? Right? If you trace back all the light rays to where it looks like they came from, it should look like all of the light rays come from the object location. And that's because the light rays are actually coming from the object location. Okay, so for this question, to find the answer, you need a position where the light rays are entering your eyes and where it looks like the light rays are coming from the image location. So think about that and I will give you the answer later. And this is the same question, but now you have a converging lens where the object is located between the focal point and the lens. Using the hints from the previous two questions, you should be able to figure this one out, so think about it and I'll give you the answer later. Now that we all perfectly understand single lenses, let's talk about lenses in combination with other lenses. The short of it is that you have to repeat the single lens procedure twice. This means that for each lens you're going to use the lens equation, so you'll use it twice. The long of it is that the image that you get from the first lens will become the object for the second lens. So let's take a look at how this works in practice. In this figure, I have an object, I have a diverging lens, and I have a converging lens. The focal points for the diverging lens are located here and here. And the focal points for the converging lens are located here and here. To deal with this situation, the first thing I want to do is ignore the second lens completely. So that brings me back to a single lens case. To deal with the single lens case, I want to draw the ray diagram for a single lens. I'm just crossing out the things I don't need just to keep track of everything. Okay, so let's draw the first easy to draw ray for this diverging lens. That's the horizontal focal point ray. So you start with the horizontal. It's a diverging lens, so you know that the ray has to diverge somewhere after it refracts. To find out exactly where it diverges, you have to make it look like it's coming from the focal point. So then that horizontal ray will refract upward in this direction. The next easiest to draw ray is the third easy to draw ray. So we will draw the ray that starts at the top of the object and goes straight through the center of the lens. And that one just goes out like that. Okay, so then these two rays, the outgoing rays do not meet, but if you trace them backwards, it looks like they're located right here. Okay, so we've determined the image for the first lens. Now we want to use that image as if it were the object for the second lens. So I'm going to take that image and I'm going to translate it down to the bottom figure. We found an image that was located right here. Okay, the second lens here is the converging lens, so I'm going to completely ignore the diverging lens. We've already found the effect of the diverging lens, so we can now ignore it. The original object, we've already dealt with that, so we can ignore that. We can ignore the focal points for the diverging lens, and we're left now with an object, the converging lens, and the two focal points for the converging lens. So now I just do the single ray diagram, or the single lens ray diagram for the converging lens. I start with the horizontal ray that hits the lens and it refracts through the focal point. So that is the first easy to draw ray. The second easy to draw ray is, again, the third easy to draw ray. This one starts at the top of the object. It passes right through the center of the lens, and it doesn't refract at all. Okay, so then the object now passes through that lens, or the rays pass through that lens, and they converge at a single point on the right side of the lens. This is the image location for it's the image location for the object that we were just using, but it's also the image location for the original object after it has passed through both of the lenses. This is something that's useful to study because we actually use it a lot. Telescopes and microscopes, for example, use two lenses in combination to form an image. Even if you wear glasses, then the lens of your glasses and the lens in your eye work together to form an image on your retina. The figure at the bottom shows a compound microscope where you start with an object. The light rays pass through the first lens, which is called the objective lens. An image is formed between the objective lens and the eyepiece lens. And then the rays that come from the object and then form the image continue going through the eyepiece lens until they reach your eye. To your eye, if you trace back these rays, it will look like they're coming from an image location all the way back here on the left. So you start with an object that's very tiny. You end up with an image that's very large in comparison. Common microscopes and telescopes might be able to enlarge an image by 100 or a couple hundred times, but compound microscopes and even more powerful microscopes can actually magnify an image to be 2,000 or more times larger than it initially is. Notice in this case that the image that's formed by this combination of lenses is actually a virtual image. The outgoing light rays do not actually meet at the image location. So when you're looking through these two lenses, the image that you see is virtual. So again, don't be confused by this wording virtual, this term that we use. It's still an image that you actually see when you look through the two lenses. In the front of the human eye, there is a lens. Along the back of the human eye is the retina. When images form on the retina, the signal is transmitted to the brain, and this is how you see. In order for an image to form on the back of the eye, horizontal light rays must be bent together and focused into an image on the retina. Because of this, the lens in the human eye has to be a converging lens. For most people, the distance between the lens and the retina is about 2 centimeters, and this distance is fixed. However, objects at different distances from the eye will focus at different locations along the back of the eye. In order to see clearly, you need that focus to be on the retina. In order to do this, the muscles in the eye can adjust the lens in a process called accommodation. During this process, the actual focal length of the lens changes. To talk about the human eye, we define 2 points. The first one is the near point. This is the shortest distance in front of you where you can clearly see an object. So for this eye in the lower right corner, if your near point is at this blue dot, then anything to the left of this blue dot you'll be able to see clearly. Anything to the right of the blue dot will be blurry. For a normal human eye, or a human eye with normal vision, this distance is about 25 centimeters, or so I'm told. If your near point is further away than 25 centimeters, so at this yellow or orange dot right here, then you have what's called hyperopia, or farsightedness. This is just when the near point is further than normal. The second point we define is the far point, and this is the furthest distance you can see clearly. For normal human vision, the far point is out to essentially infinity. Basically, no matter how far you look, you will see an object clearly. So if you look up in the sky and you see the moon up there, you should be able to see it clearly. If you have nearsightedness or myopia, then your far point is closer than infinity. So in the picture down here, your your far point might be located at this yellow dot. Then anything past this yellow dot, you will not be able to see clearly. Anything to the right of the yellow dot, you should be just fine seeing. So then if you have hyperopia, the range that you can see clearly is everything past this dot. If you have normal vision, then everything you can see clearly would be past the blue dot. If you have only myopia, your range of vision would be between your far point and your near point. And if you have hyperopia and myopia, then your range of clear vision would be even smaller in this range. Okay, this is the kind of question that I would throw into the lecture to see if you were paying attention on the previous slide. But since here you can just rewind the video 5 seconds, I'm not sure if this hits the same spot. But in any case, question. If the near point of your eye is at 75 centimeters, you are... Well, the normal near point is 25 centimeters. So if your near point is at 75, it's much further than the normal near point. Therefore, you cannot see things close to you clearly, and that makes you farsighted. The process of accommodation, where your eye's focal length changes, this is what allows you to see things clearly in your range of vision. However, the ability for your eye's lens to accommodate cannot be changed. There's only a certain range where the eye can see normally. You can't make your near point closer to you or your far point further from you naturally, at least not without surgery or something along those lines. Note that over long periods of time, generally speaking, as you age, your eye's ability to accommodate does deteriorate slightly. This is called presbyopia, and it's the tendency to become farsighted as you age. Your near point tends to push out a little bit the older you get. This is why older people tend to wear reading glasses. And generally speaking, to correct these types of vision defects, you can use lenses, and this is why people wear glasses, of course. The purpose of the lens is to create an image within the natural near and far points of the eye. So basically, you're going to make faraway objects seem closer or nearby objects seem further. So let's take a look and see how this works. Let's say you're hyperopic. So you have a near point that's a bit further than the normal near point. And let's say you're trying to read a book that's close to your eye, where the arrow there represents a book. In order to see this book clearly, you can use a converging lens close to your eye, and the light rays from the lens So let's take a look at how this works. Let's say you're hyperopic and your near point is a little bit further than the normal near point. Let's say you want to read a book and you bring the page close to your eye, where that arrow represents the book. In order to see this book clearly, you can put a lens in front of your eye, and that lens can create an image of this object. So if this is the object, the lens can create an image of this object at your near point. This is the case of a converging lens, where the object is between the focal point and the lens. So you can go back to the ray diagram to see specifically how that works. But basically, the object is close to your eye, and the lens projects an image further away. The image is enlarged. So if you've ever looked through a pair of reading glasses, you've noticed perhaps that the image that you see through the glasses is larger than usual. So even though you can't see this object clearly when it's close to your eye, the lens projects an image further back within your normal range of vision. Then your eye sees that image and it can focus it clearly on the back of your eye, on your retina. So then you can see that image clearly. On the other hand, if you're myopic, let's say you're trying to look at a tree in the distance. So you're trying to look at this tree that's very far away from you, and your far point is closer than usual. In this case, you can use a diverging lens. The diverging lens will take this object that's far away and pull it closer, essentially. It'll create an image at your far point. So this is the case of a diverging lens. You can look up the ray diagram to see how this works. But for all diverging lenses, you have an object, then you have an image that's pulled closer to the lens, and it doesn't matter where the focal point is. So again, you have an object that's outside of your normal range of vision, so you cannot see it clearly. The lens creates an image that is within your normal range of vision. Your eye can then see that image clearly, so it can focus the light rays on the back of your retina. And this left case was for diverging lenses. So in short, if you are farsighted, then your eyeglass lenses are converging lenses. If you're nearsighted, then your eyeglass lenses are diverging lenses. If you are both far and nearsighted, then you would have to wear something like bifocals in order to see clearly at all distances. And I wanted to just flash back to this first slide real quick, because all the lenses I've been drawing so far have been either this type of convex lens or this type of concave lens. And if you have eyeglasses, you're probably thinking to yourself, well, my glasses don't look like that at all. Typically, eyeglasses fall into this second column of lenses for the converging and diverging lenses. And the reason for this is because it's more comfortable to wear them when they bend outwards slightly. But notice the similarities. In the case of a converging lens, they are thin on the outside and thick in the middle. And that is the same as in the second image here. Thinner on the outside, thicker in the middle. For a diverging lens, you are thicker on the outside and thinner in the middle. And this is true also in the second column. Thick on the outside, thin in the middle. Okay, so now suppose that your far point is 30 centimeters from your eye and your near point is 10 centimeters from your eye. This is maybe typical of somebody who has myopia. So their far point is much closer, but also their near point tends to be a little bit closer as well. Okay, so now in order to correct your vision, you need glasses that create images of very distant objects that are what? It's a fairly straightforward question, but think about it and I'll give you the answer in one of our meetings. This question just asks what kind of lens can create an image between the object and the lens. So this is something that we talked about a few slides ago, but you can also go back to the ray diagrams and check. I will leave that to you and give you one of the answers later. And this question is similar. What kind of lens can create an image behind the object? So on the same side of the lens as the object, but further away from the lens. Think about it, and I'll tell you later. This slide sums up what I was explaining a few slides ago. So basically, if you are nearsighted, this means you cannot see things that are far away from you, clearly at least. So you have to take those far away objects and bring them closer to you. So then you need to create an image at the far point. Diverging lenses can do this. They can pull the images closer, and it's shown in the ray diagram on the top here. So you have to imagine your eye being on the right side of this ray diagram. You're trying to look at an object that's far away. You can't see it clearly, but the lens will create an image that's closer, that you can see clearly. And then if you're nearsighted, the opposite is true. Your eye would be on the right side of this diagram. You're trying to look at something that's too close to you, and you cannot see it clearly, but the lens pushes the image back further so that it's at your near point. Then you can focus on that image and see the object clearly. So this is another one of those "are you paying attention" questions. It asks, so if your vision is improved with lenses that look like the ones shown here, then you must be which of the following? To answer this question, you have to identify the kind of lens that this is, and then just determine which type of vision defect this lens corrects. If you're not sure of the answer, why don't you go back a few slides and try to figure it out? But if you are sure of the answer, then you should know that it is B, myopia. So again, if you are nearsighted, then you have diverging lenses to correct your vision. Here's a graphic that I added to show you the range of clear vision for normal eyes and a myopic eye and how it gets corrected. So for a normal eye, the near point is generally about 25 centimeters, and anything to the left of that you can see clearly. For a myopic eye, this means you're nearsighted. That means you cannot see things far away, so the furthest you can see is maybe 50 centimeters if that's your far point. So anything to the right of this you would be able to see clearly all the way up until your near point. For a myopic eye, your near point is typically closer than the 25 centimeters for a normal eye. So your range of vision would be this range right here. When you put a diverging lens in front of your eye, that lens creates images of all the objects that you see further away. So it pushes all the images back. So this actually pushes your far point back to infinity if your prescription is correct. Since it's pushing all of the images back, your near point also gets pushed back to that normal 25 centimeters, or roughly 25 centimeters. So with a diverging lens, your range of clear vision is the same as for a normal eye. And one thing to note here, actually, if you are myopic, maybe you can't see things that are far away clearly, but your near point is typically closer than that of a normal eye. So you can usually see things closer to you better than quote-unquote normal people can. And also, if you are myopic, you may have noticed that if you try to read something very close to your face while you're wearing glasses, it might make you uncomfortable and you might have to remove your glasses to read it clearly. This is because when you're wearing glasses, your near point is pushed further away. When you remove your glasses, you have that extra range of vision that you didn't have when you were wearing those glasses. Yeah, plus you get to wear cool glasses, so see, myopia, not all that bad. And actually, this is something you might want to consider if you're thinking about getting LASIK. When you get LASIK, they will fix your eyes so that you will have this normal range of vision, but your near point will be pushed further away. Generally speaking, I suppose you should speak with your eye doctor about that rather than your physics professor. But this is my understanding of it in any case. The reason for myopia is that the distance from your lens to your retina is too long. So this is shown in the image here on the top left. The distance between the lens and the retina is too long, so the light rays focus at a point too close to the lens. And then when the image forms on the retina, it's not clear, it's blurry. In order to fix this, we use a diverging lens to spread the light apart just a little bit. So when those horizontal rays come in, you want to spread them apart a bit, and then when the lens focuses the light, it will focus it on the back of the eye. And hyperopia, of course, is the opposite of that. The distance from the lens to the back of the eye is too short, so when the lens tries to focus the light, the image is formed behind the retina. To fix that, you need help bending the light together. So you put a converging lens in front of your eye. This bends the light together a little bit, and then your eye's lens can bend the light the rest of the way. Then the image can form clearly on the back of the eye. And that's all I have for you today. I hope you enjoyed Chapter 23. If you have any questions, please let me know. Otherwise, have a good one.